So in this lecture, we're going to introduce the basic definition or the formal definition of linear maps, and then we're going to show how this applies to matrices, and we're going to introduce a few other definitions for the different types of invertible maps. For the different types of maps: invertible maps, injective and surjective maps. And we will end with showing the rank 1 operators and square matrices, and finally with the composition of linear operators. How do you multiply matrices by each other? So the basic definition of linear operators or linear maps: a linear map T between two vector spaces is a function T that's defined from the first vector space to the second vector space. It maps every element in V to an element in W, such that for every two elements in V, and for any two real numbers, the function of the linear map on the linear combination alpha x plus beta y is equal to alpha multiplied by tx plus beta multiplied by t of y. And if you try this on matrices are examples of such linear maps. Now, a fact that we are not going to prove in this course, it's beyond the scope of this course, is that any linear map between Euclidean vector spaces can be represented by a matrix of numbers. Of course, you have to choose the basis vectors and all that, but we're not going to go through this. But you just need to know that if you have a matrix that is equivalent to a certain linear map, and if you have a linear map, there is a representative matrix. So the next thing we want to discuss is, since it's a function, we want to understand whether this function can be inverted or not. Can I find the inverse of the function if this function takes me from one vector space such that for any vectors here, this is a function. Let's call this a linear function. This linear function t. If this vector is transformed to this vector, and if this vector is transformed, for example, to this vector, let's add a little bit of color. The blue goes to the blue, and the green is transformed to the green. The question is does the inverse of the function exist? Or in other words, for any vector in this vector space, can I find the pre-image of this vector? Can I find a function that would give me the source vector before applying t? So we're looking for to find which matrices can be invertible. Now, to understand which matrices can be invertible, we have to understand the kernel, or we have to first define the kernel of a matrix. What is a kernel of a matrix? I'm going to show you the kernel of a matrix using an example. Let's look at the matrix M is equal to 0, 0, 0, 1. And let's see what this matrix does. Now, we know from our elementary linear algebra that this matrix is not invertible. I cannot find m minus 1. But let's understand what this actually means, that I cannot find m minus 1. So let's just start with a vector. This vector, let's call it x0. What will happen when I multiply m by, let's call this vector x. What will happen when I multiply m by x? 0, 0, 0, 1, multiplied by x1, 0, I'm going to get a 0 vector. Which basically means that this blue vector goes to the 0 vector. Okay, what will happen if I multiply m by y? Let's pick y to be 0, y1. This will be equal to 0, y1, which means this is my, and mx is equal to the 0 vector. Which tells me that there are some vectors here that end up going to the 0 vector. In fact, any vector along this axis will end up going to the 0 vector. Now, let's try to find the pre-image. So, if this is m, the function of m, let's try to understand, does m minus 1 exist or not? Can I define m minus 1? Now, for my, if I call this z, I can say, okay, well, y was the original or the pre-image of my, or the pre-image of z. But let's try to look at 0. What is the pre-image of 0? Well, there are so many vectors here that are the pre-image of 0, because the 0 vector itself, if I multiply m by 0, I'm going to get the 0 vector. If I multiply m by x, I'm also going to get the 0 vector. If I multiply m by negative x, I'm also going to get the 0 vector. So this is m0, and this is also m multiplied by the vector negative x. In fact, this is m multiplied by the vector negative 5x, which is also equal to the 0 vector, m multiplied by any number multiplied by the vector x. So, which tells me that I'm not able to go back from that 0 vector, which means m minus 1 is not cannot be defined. M is not invertible. So it turns out that for me to find out whether a matrix is invertible or not, all I have to do is find out how many vectors, when I multiply m by those vectors, I get the 0 vector. So let me write this down. It turns out to know whether a matrix or a linear map in Euclidean vector spaces is invertible or not you need to count how many vectors, and I'm just going to put brackets around count because there are probably, if there's one, there's if there's one non-zero, there's infinite non-zero vectors. So you need to count how many vectors are mapped to the 0 vector. And these vectors that are mapped to the 0 vector. So again, these vectors that are mapped to the 0 vector are called the set or the kernel set. And the definition of a kernel, the formal definition, starts by we first define a linear map. The kernel of this linear map is a set of vectors, not any vectors. These are the vectors that T take to the 0 vector. Let's find an example, or let's solve an example. Find the kernel of the following matrix. We need to find the set of vectors for which M will map these vectors to 0. So M is equal to this matrix is equal to 1, 1, 2, 2. Let's try I would like to know mx equals 0. What are the possible x's? So I know from experience right away I can put here negative 1, 1. And this will give me 1 multiplied by negative 1 plus 1 multiplied by 1. 2 multiplied by negative 1 plus 2 multiplied by 1. Which will give me 0, 0. Therefore, the vector negative 1 and 1 is one of the vectors in the set kernel of M. What else? In fact, if I put here any vector of this form, where alpha can be any number, 5, 6, 7, 100, any number, I will find 1 multiplied by negative alpha plus alpha, negative 2 alpha plus 2 alpha. Again, this will give me 0, 0. In fact, negative alpha and alpha is in the kernel of M. And you're going to find that the kernel of M is in fact equal to the vector x, where x is the vector made out of negative alpha, alpha, and alpha is any real number. Now there are functions in Mathematica that give you right away the kernel, and we're going to introduce this in another lecture when we talk about the Mathematica functions that apply to matrices. This is a bonus exercise for those who are mathematically inclined and would like to prove that using the properties of a linear map, prove that the kernel of a linear map is a subspace of V. Now this should be a simple exercise, so try it out, and if you have any questions, you can let me know. So it's very important now to understand when is a matrix invertible and when is a matrix not invertible. Now before we explain or we jump to the invertibility of matrices, we would like to define a few functions. Or first one is injective maps, and I would like to start, rather instead of the definition, I'm going to start with an example. Let's assume that this is the set of CV398 students. And I have a set of all possible IDs, student IDs at the University of Alberta. Now, for every student here, there is a unique ID. No two students share the same ID. This is an example of an injective map, one-to-one. It's a map that assigns a unique result to the argument of the function. So this map or this function, injective map, assigns a unique result to its argument. Formally, how can I write this? Let T be defined a map from X to Y. T is injective if for every X in X there exists a unique Y in Y. I'm using the exclamation mark here to indicate that this Y is unique such that T of X is equal to Y. So for every X there's a unique Y. For example, CV398 and all the possible IDs. Now, I cannot find an inverse to this map because there are some IDs here who, if I try to find a student in CV398 that corresponds to this ID, I am not able to find such a student. So I'm not able to invert this map. The other kind of map that we're going to study is a surjective map. And again, I'm going to introduce it with an example. Students in CV398 and gender. Male, female. Every student in our class will either be a male or a female. And we usually have all the possible genders. So, since we have both males and females in our class, this is a surjective map, which means that the range covers all the codomain. If I call this the domain of the function, this is the codomain. Range is equal to the codomain. Where the function reaches is also equal to the whole codomain. So to formally define this, T from X to Y is surjective, then for every Y in Y, I'm covering all the possible Y's here in the codomain. For every Y in Y, there exists at least one X such that T of X is Y. Okay, so we have looked at the injective maps, the surjective maps. Surjective is also called onto. An invertible map, a map which for every element I can assign another element in the codomain, and for every element in the codomain I can assign or I can find one element in the domain, or as the pre-image of that element. Such map is called bijective or invertible. I can invert it, and I hope you have already guessed that an invertible map is just a map that is both injective and surjective. So an invertible map, the definition is that is both injective and surjective, or injective also is called one-to-one, and surjective means onto. So how does this apply to matrices? I'm not going to prove any of the arguments that follow, but an invertible matrix is the matrix whose vectors, non-zero vectors, always have a non-zero image. Let me write this down. All vectors have all non-zero vectors have non-zero images. Therefore, matrix is invertible. I'm able to find the inverse. Now, I haven't really told you how to find an inverse yet, and that has to do with the determinant and all that, but we're going to study this later. We're just trying to understand the basics behind matrices right now. And then a non-invertible matrix is a matrix that takes some vectors and put them along a line here, and some other vectors go to the zero vector. So some non-zero vectors are mapped to the zero vector. Therefore, matrix is not invertible. All right, so these are facts. You can try to prove them, but they might be a little. They might take some time. But the fact is, a linear map is invertible if and only if the kernel of T is the zero vector. So again, a matrix that is n by n is invertible, or I can find its inverse if the kernel T, or the kernel of this matrix, or the vectors that M will take to give me the zero vector, these vectors are only one vector. There's only one in this set, which is the zero vector itself. So now we're going to introduce the matrices from the bottom up to talk about what do the different rows in the matrix represent. Because a matrix is made out of different rows. What does each row mean? And we're going to see that each row represents what we call a rank 1 operator. And we have as many rows as the rank of the matrix, or as many linearly independent rows. These are the rank of the matrix. So matrices from the bottom up. What are rank 1 operators? Rank 1 operators are linear functions whose codomain is a real number. For example, T is a linear map that takes any two-dimensional vector and give me a number. Now T of x, now x belongs to a two-dimensional vector space, which means x has two components, x1 and x2. I can write this linear map v1 x1 plus v2 x2. Now let's look at the vector v, which is equal to v1 and v2. So this is the vector v. So you can look at this operation as if you're taking the dot product between the vector v and any vector x. So when I take the dot product of v and x, because the angle here is less than 90, I'm going to get a positive number. When I take the dot product between v and y, which is perpendicular to v, I'm going to get a 0. And when I get the dot product between v and z, I'm going to get a number that's less than 0. And so this is what a rank 1 operator is. It's a linear function that for any vector here, it's almost like taking the dot product between that vector and v, and I will get a number that's either greater than 0, equal to 0, or less than 0. Now, it's clear that this matrix, this linear function, is not invertible because I cannot find one pre-image of, for example, the 0 vector, because any vector along this line, if I take the dot product between this vector and v, I'm going to get the 0 vector. In general, a matrix is made out of rows, and each row represents a vector, and when I multiply the matrix by another vector, if I call this vector v1, v2, and the last vector I call it vn, then when I multiply m by the vector x, I'm taking the dot product between v1 and x, v2 and x, and vn and x. And each one here gives me the dot product between that vector and the vector x. And again, this is a bonus exercise, but it's a fact that this matrix is invertible when these vectors, the n vectors, that form the matrix M are linearly independent. Again, to prove this would take a long time, but you should perhaps on your spare time try to prove these arguments. But for this matrix to be invertible, if the n vectors that form the matrix M are linearly independent, then M is invertible, and vice versa. If M is invertible, then the n vectors are linearly independent. Now there are a few examples here that you should go through just to elaborate on the concepts that we are represented in this section. And so in the next, at some point we're going to discuss the Mathematica functions. So after presenting all the lectures on the matrices, we're going to discuss the Mathematica functions that you can use to find the kernel and to multiply matrices and multiply matrices by vectors and all that. The last thing that we're going to discuss here before the next in this portion of the lecture is how can I multiply matrices by each other, or what does it mean that I'm multiplying matrices by each other? So in general, the function of a matrix is that it takes a vector x and give me a vector mx. Another, if I take that new vector and then I multiply it by another matrix n, so n, which is another matrix that takes from this, let's say this is R2 to R2 to R2. If I take this new vector and multiply it by a new matrix, I'm getting a new vector that's equal to n mx. And usually the question is, can I find a matrix that represents the function of nm? So basically, what is the matrix that would give me this new result? nm multiplied by x. And this matrix, as you have studied before, is L, that's equal to nm. And to find this new matrix L, if this is n and if this is m, we multiply the rows by the columns to get a number, the rows by the columns to get a number, and so on. And so this concludes this portion of the lectures, and in the next portion we're going to discuss the special matrices that are square matrices and are two square matrices of size 2 and 3.